The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, so this hour we're going to talk about SIMD programming with Cell. First I'll talk a little bit about what SIMD is, and then about the facilities that Cell and the compiler provide for programming with SIMD, and then some design considerations that you have to keep in mind when you're doing things. All right, so the situation these days is that most compute-bound applications are running through a large piece of data and running the same computations on it over and over again, or rather running the same computations across all the pieces of different data. And very frequently, there will be no dependence between iterations when you're going through this data. So that means there's opportunities for you to data parallelize. So as an example, if we have, for example, say we're multiplying A0 and B0 to get C0. And suppose we want to actually perform this operation across all the elements of arrays A, B, and C. So instead of multiplying two elements or two integers together, we're actually going to be taking two arrays and element-wise multiplying each of the pairs element-wise and writing the results to a third array. So the picture is going to look something like this. And you would, of course, represent this using, for example, a for loop. Now, what we're going to do is, instead of, let's see. So you can think of this as kind of an operation that's abstractly operating on these entire arrays. And we're not going to go quite that far. But what we're going to do is we're going to think of these operations as acting on these kind of bundles of elements. So we're going to bundle our array elements into groups of 4. And then each time we're going to take a group and multiply it with another group using this element-wise multiplication and write the result to this third bundle. OK? Does that make sense? Now, the thing about this kind of model is that Cell is going to provide very good hardware support for something that looks kind of like this.
Is that actual Cell code?
Yes, I'll get into this. In fact, this is what we'll be talking about, kind of the syntax and meaning of this kind of thing. All right? So, OK, so for this kind of thing to happen, we need the compiler to support two different things. First is we need to be able to address these kind of bundles of elements, and these are going to be called vectors. And second, we need to be able to perform operations on these vectors. So Cell and the XLC compiler give us support for this. And what they're going to do is provide, first, registers which are capable of holding vectors. Now, normally, you think of a register as holding, on a 32-bit machine, one machine word will hold, a 32-bit int, for example. What we're going to have on the Cell is these 128-bit registers, which are going to be able to hold, for example, 4 ints right next to each other. So we're going to be able to take kind of this bundle of ints and operate on it as a unit. And the second part is we're going to have operations that act on these vector registers. So the Cell is going to support special assembly instructions, and it's going to be able to interpret those as acting on particular vectors. But also, we're going to have C++ language extensions, which are called Intrinsics. And those are going to give us access to these special assembly instructions, but not require us to be poking around in the assembly. All right. Now, the big draw of this is that these operations are going to be pretty much as fast as single operations, which means if we take advantage of them, we can make our code run, say, 4 times as fast. OK, so how do we kind of refer to these vectors when we're coding? XLC is going to provide us with these intrinsics, and we have these vector data types. And each one is just going to specify kind of how to interpret a consecutive group of 128 bits as some sort of vector. And you can have vectors of varying element sizes and varying number of elements. So when you're programming on the PPU or the SPU, you get these 4 different kinds of vector data types. You can declare things as, for example, vector signed int, which is what I mentioned in the example, which is where you have 4 ints next to each other, each 32 bits. You can also have vectors which contain 16-bit integers or 8-bit integers. And you can also have vectors of floating point numbers. I should mention that all of these signed integer types also have unsigned equivalents. Anyway, so you can just declare these anywhere in your code and use them as if they were a C++ data type. All right, any questions? On the SPU, you also get some additional vector data types. One is vector signed long, which is 64-bit ints, and you can fit 2 of those in 128. And you can also fit 2 double precision floating point numbers in 128 bits. Now, the compilers actually support these types pretty nicely. So not only can you declare variables of these types pretty much anywhere in your code, you can also declare pointers to these types and arrays of these types. All right? And so they look pretty much like natural C++ types, except that they translate directly into these particular types that the hardware supports. All right? Now, in order to manipulate these vector data, we're going to have compiler extensions called Intrinsics, which are going to provide access to the assembly level features that we want. Remember, we're going to have specific assembly instructions that correspond to, for example, multiplying two vectors which contain each 4 32-bit integers. And instead of going into the assembly and actually inserting that instruction ourselves, we just use a compiler intrinsic inside our C++ code. And what it does is it provides this notation that looks a lot like a function call, but the compiler automatically translates it into the correct assembly instruction. And again, you don't have to worry about going into the assembly and messing around with this instruction is supposed to apply to these registers. You don't have to worry about register allocation at all. The compiler just figures out the right thing for you. And to use these in your SPU program, you're going to want to include SPU intrinsics.h. Now, what's a little bit confusing is that you're going to have slightly different intrinsics available on the PPU and the SPU, because those are actually going to have different instruction sets. But anyway, as an example, you can declare two variables of type vector signed int, and then you can multiply them using this intrinsic called SPU add. All right, and assign them to a third vector signed int. Questions? Yep.
In what way are the intrinsics different on the SPU and the PPU? Is it just not entirely the same set of operations available, or are there actually semantic differences? You could make a little header file that masked over the differences mostly?
There are going to be some operations that are only available on one and not the other. But in general, if you look at the names, if the names correspond, and I'll go into that in a little bit, then they should perform essentially the same function.
Mostly was the key word in what you said. There are definitely some differences. There are also some name differences where there really don't need to be. For instance, if you try to do a shift on the PPU, I believe it's SL, shift logical right, shift logical left, or shift arithmetic right, sort of things you would sort of remember. On the SPU, it's the acronym for rotate and mask for shift. So, ROTMAR, something like that too. So, yes, there's some differences that don't need to be there.
All right. OK, so to actually create these vectors, there's a couple of different notations you can use. The first is you can use this thing which looks like a cast to, for example, vector signed int. So you do vector signed int in parentheses, and then a list of 4 integers you want to fill in. And that will create an integer vector and assign it to A. You can also, I believe you can also use that notation with just one integer, and it will fill in that integer in all 4 positions. There's also an SPU intrinsic called splats that you can use to basically copy the same integer to all 4 components.
How does it know you're not using the comma operator?
Yeah, I don't know. Is that right, David, with the parentheses in the second part? OK.
Whatever.
Another caveat here from someone who's been in the trenches is that XLC likes this notation. GCC sometimes likes curly brace notation instead.
So I'd seen both of
if you're
those, and I didn't know
initializing-
which.
Curly brace also works, I suppose. The curly brace also works as
OK, great, thanks. All right. And after you've assigned some of these variables, in order to get back the pieces out, one way you can do it is to use this kind of union trick, where you assign, or rather you allocate something of vector signed int, and then you tell C++ that it can find an array of integers in the same place. And what that will do is pull out the components. So if you define this union in this way, then you get a type called intvec. And anytime you have an intvec, you can either do .vec to get at the vector signed int, the vector data type, or you can use .vals to, with an array index, get at the components of the vector. All right? And you can also use this intrinsic called SPU extract to pick out the same components. XLC provides a bunch of different vector operations that you can use. There's integer operations, floating point operations. There are permutation and formatting operations, which you can use to kind of shuffle data around inside a vector. And there's also load and store instructions. And I believe we have a reference linked off the course website if you want to figure out more about these. I'm only going to touch on a few of them. OK, so the arithmetic and logical operations, like I said, most of these are the same between the PPU and the SPU. There's some that are named slightly differently, and some that are not available on the PPU. So these are all the things you would expect. Add, subtract. Mad is multiply and then add with three arguments. Multiply, RE is for reciprocal. You can also do bitwise and or XOR, and I believe there are other logical operations there too. Now the thing is, you have to worry about which PPU or SPU instruction you're using, but you usually don't have to worry about selecting the right vector type. The compiler should figure out which vector types you're using and substitute the appropriate assembly instruction that produces a result of kind of the same vector type. So all these operations are what we call generic, and they kind of stand in for all the specific instructions which only apply to a single vector type. Does that make sense? OK, so one handy thing is a permutation operation, and this allows you to kind of rearrange the bytes inside a vector or 2 vectors arbitrarily. And so the syntax is SPU shuffle A, B, which are your source vectors, and pattern, which tells you how to shuffle them. And pattern is going to be interpreted as a vector of 16 bytes. And each byte is going to tell the compiler how to pick out one of these bytes in the result. And how the byte is interpreted is the low 4 bits are going to specify which position the source is going to come from, and the 4th bit is going to specify whether you're going to pull from A or B. So as an example, here's the pattern VC, and if you look at the second byte, which is 1, 4, in hex, then that means the destination register is going to contain the fourth byte, or the fourth byte of B. All right. So 4 means select the element numbered 4, and 1 means select from B. Does that make sense? And this is very versatile. By putting in the right pattern vector, you can arrange for all these bytes to be shuffled around however you want. Pardon?
The pattern is a constant, an immediate parameter.
You can fill in the parameter at runtime, if that's what you're asking.
It's like a for construct.
Yeah, you can construct a pattern within pipe.
Yeah. Okay. Also useful are these rotation operations, which will let you shift your vector left or right by some amount. Now, one thing to beware of is that on the SPU, you only have these 128-bit registers. So on the PPU, you have different registers which are suitable for holding different types. For example, there's word-sized registers for holding ints. And the PPU also has these 128-bit registers, but the SPU has nothing else. So that means whenever you're using scalar types on the SPU, they're all going to be using these large registers, no matter what the size of the scalar you're using. And depending on the size of the scalar you're using, it's going to go in a particular position inside this this wide register. It's called a quad word register because it's 16 bytes. Now the thing to watch out for is that whenever you load something from memory into, whenever you load a scalar from memory into one of these registers, there's going to have to be a little extra processing done in order to possibly shift the scalar into the right place inside this register. And furthermore, the hardware is always going to want to grab one of these quad words all at a time. So loading a scalar is not going to be any cheaper than loading one of these quad word registers. So when possible, you're going to want to load an entire quad word register at a time. And if you just need a part of it, then you can figure that out later. But you might as well get the whole thing. Questions? Yep.
So when you actually, just this is a scalar question. So when you load a scalar value that's not aligned with the preferred position, is there overhead associated with that?
I'm not sure how much overhead is associated with that. Pardon? Oh, do you know?
Load an unaligned scalar, it can only load on 16-byte boundaries. So it's going to load something that includes that, and then it's going to have to shift it into position.
So do unaligned, when it has to shift the scalar around, does that actually take longer than when it's natural?
I don't know if it's, well, what you can do, you can set some flags to XLC that say, align all of my scalars correctly, and will waste 4x overhead. It will even say align my array, pad my array elements, so that I can have a scalar array that I can load, and it will waste the overhead so that everything in the array is aligned. So you can have the compiler trade off space versus time for you on some switches.
I see. Okay, so we're going to want to look at the sim application from Recitation 2, and we want to adapt that to make use of SIMD data types and intrinsics. So what we've done is, remember we had these XYZ coordinates that we were manipulating. What we're going to do is we're going to pad each one. It was 3 words before. We're going to pad each one so that it fills a quad word. And so for each quad word, of course, the first 3 words are going to correspond to the XYZ components. And we can grab those out using SPU extract or some other intrinsics. Now, when we're doing manipulations with these components, for example, we wanted to find the displacement between 2 locations, and that's just subtracting 2 of these coordinates. So we can do that subtraction, which before required 3 floating point subtractions. We can replace that with a single SIMD instruction. Does that make sense? Okay, so all right, so all of this, most of this has already been done, and we're providing most of the implementation of this SIMD version of Sim. And what we want you to do is download this, download the tarball for this recitation, and then go in there. And what we want you to do is fill in one of the blanks. All right. So there's just one function here that's been left unimplemented. And to see if you know what's going on, see if you can fill in the implementation for this. Any questions? So this function you want to implement is basically going to take a vector float, and if that float contains A, B, C, and D, you want to return a vector which each of whose elements is A plus B plus C plus D. Questions?
What directory under the
Yeah, so we're going to go into Sim AOS.
We can stay around afterwards and help you figure out what's going on.
Yeah. Okay, so here's one implementation. Basically, we're going to just declare another vector float, and that vector float we're going to that's basically we're just going to do these swaps. So notice in this one we're swapping the first and second words. So that means down here we're going to want to carry bits 4, 5, 6, 7, and then, or bytes 4, 5, 6, 7 first, and then bytes 0, 1, 2, 3. And then over here we want bytes 12, 13, 14, 15, and then 8, 9, 10, 11. So everyone see what's going on for the first shuffle? And then we're going to just add that to our original vector to get this. And we can do that again. This time now we just want to swap these two halves. So the shuffle pattern is going to be 8, 9, 10, 11, 12, 13, 14, 15, followed by 0, 1, 2, 3, 4, 5, 6, 7. Make sense? OK. So the way we translated the program we just used into SIMD was we used a struct of arrays. Basically, each of the structs that we had from our previous implementation just carried over, and we just put all of those into an array, so the structs were right next to each other. Alternatively, we could have laid out the data in memory in a different way, and this is called an array of structs layout. Instead, what we can do is kind of put all the like fields next to each other, so that we have, for example, an array of all the x components, then an array of all the y components, then an array of all the z components. And when you kind of reorder the data this way, you get kind of different ways you can use to process it. So for example, now each quad word, instead of containing the data for a single point, is going to contain the data for the same component of 4 consecutive points. Everyone see that? And actually, we can implement the algorithm from before in this new layout. But we have to be a little bit more clever in how we're putting together the elements. Before, we were able to just kind of subtract or multiply the quad words with each other, because those would just correspond to, for example, subtracting the coordinates of 2 points. Now this time we have to kind of do some additional computation in order to put all the pieces together. Kind of the trick behind this structure of arrays implementation, which I'll just sort of gloss over, is if we're storing state for 8 objects, then we're going to need 8 objects hold let's see, 24, or rather, for each object we need the position and the velocity, and for each of those we have x, y, and z. So that means to store state for each object, for 8 objects, we need 8 times 6 is 48 words. And so we can put those in 12 quad words if we pack them right. And when we do kind of SIMD operations on these quad words that we pull out, we can get 4 pair interactions. So suppose this is a quad word and, it contains data corresponding to elements A, B, C, and D. And over here we have a quad word containing data corresponding to elements 1, 2, 3, and 4. With some SIMD operations, we can kind of figure out the pairwise interaction between objects A and 1, between B and 2, C and 3, and D and 4. But of course, we have to be able to find the interactions between any pairs, not just these pairs that line up. So what we have to do is rotate the quad word over by one word and then do the same thing again. We do that 4 times in all, and then we add up the results. So as you can see, this implementation is a little bit more involved and kind of less, it maps to the original implementation kind of less directly. On the other hand, it does give us a really dramatic speed up, kind of because we're using more of the vector words. Notice that in the first packing we had X, Y, and Z, and then the 4th blank was unused. Anyway, this time, the structure of arrays implementation is actually 7.5 times faster than the array of structures implementation. So choosing this data layout correctly can actually be, one of the really big determinants of how your program performs.
Scalar version was like what, 480, something like that, or is it not comparable?
Let's see. David, do you remember? Okay, so
that was just on the PPU.
Oh, right. So you're doing the scalar version on the SPU? Actually, it was 410 and 310 for the AOS.
For optimization, the AOS will be at 3.
Right.
oh, okay. All right, so
Where they compile with the same optimization as
Yeah,
well.
O2.
okay, so something like 400 for the double buffered one and 300 for array of structs. Okay, one other thing to worry about is when you're dealing with these SIMD instructions, you want to make sure that all your data are aligned correctly in memory. And like I said before, when you're pulling things in from memory, you want to make sure that whatever you're pulling in is going to be aligned on a quad word boundary. You can use the aligned compiler directive to tell the compiler, I want this piece of data aligned at a particular place. And if you do that on all your arrays, for example, and make sure that the array elements are going to fit neatly into quad words, then you should be OK. And again, like I said before, you also want to transfer only multiples of 16 bytes on the load and store. And so when you're doing processing, it may help you if you actually pad the end of your arrays so that they fill out a multiple of 16 bytes. Because it's easier to just do that processing with the SIMD instruction rather than just have 1 or 2 elements hanging off and have to worry about those. Yep.
Is it a good idea to pass parameters to pointer by reference or by value? I mean, which one is preferred? And then we have some key.
So you should, I think by, if you pass pointer, it'll break a lot of the analysis for figuring out whether something is aliased or not. So it might make the compiler do more pessimistic assumptions. So in cases where you can avoid using pointers, you should do that.
Okay.
But I believe, I don't know, Alan, or David, are there keywords like the restrict keyword or something that says these are unaliased?
Yeah, the XLC definitely has restrict. I believe GCC does as well.
Okay.
Restricted, I think, whatever it is.
Okay. So there are pragmas or little hints to the compiler that says passing things by pointers or but treat these things as unaliased, or if you're passing in arrays, you can say you can add a keyword that says restrict, which means it's not. You can treat it as an independent chunk of data. So you can do.
Meaning that there's no other referencing scope to the same data.
Right. But nothing else will point to the data that you've got the restricted pointer to. It's restricted to being pointed to by this particular pointer.
But it's not bounded to the local scope, it's global.
I don't know. I haven't haven't played with math.
It's local to the function where you actually apply. So if you pass in, if you say function foo, and then on parameter you say restrict a, within that function that restriction holds.
All right. So one last thing that I should mention, I haven't really let on, but compilers can actually generate some of these SIMD instructions by themselves. If you declare your types to be vector and then you use just regular operations, apparently GCC and XLC, yes, will substitute the correct intrinsics for you. Of course, that doesn't get you all of the operations which are available with intrinsics. But anyway, automatically SIMDizing your code is something that's really worth looking into. As we saw, it can give you a great performance improvement. And the thing is that compilers are still not very good at kind of automatically doing this transformation. So unlike instruction scheduling, where if you pass in 05, your compiler will do a much better job than you would have time to do. This is something that you should probably reserve some time for. All right, that's all. If you have any questions, you can stick around and I'll try and help you.